Our entry today will focus on roots and radicals, and this should be labeled entry 57 in your notebooks. We've been introduced to radicals before, the word radical, in the sense that when you graph a radical or a square root, such as the square root of x, you would see a half parabola on a graph. And this is as opposed to when you have the square of a number, a quadratic equation, you would see a full parabola on the graph. So we come to associate this square symbol, square root symbol, and the square of the exponent too as opposites, and that they cancel each other out. So let's delve a little bit deeper into these rules of radicals and how they're similar to the rules of exponents. The first thing I'd like you to do is to draw a little square up on the left-hand corner, and in a square, some important features are the area, obviously, and we know area of a square is made up of the side length, s, times the other side length, s. So when we think about the word square root, that term comes from the idea of the side lengths when you're given the side length s, when you're given the area a. So a square root is a side length of a square with the area a. So let's say you were told to find the square root of 4. That essentially means you think of a square with an area of 4, and you're trying to find the side length that will multiply together to make that area of 4. So the square root of 4 would be 2, because only a side length of 2 would multiply together to get the area of 4 if it had to be a square. So let's write down here in our definition of a square root that the square root of a is equal to s when s squared is equal to a. So the square root of a is a single number, and that number squared is equal to that area inside of that square root. One important thing to remember about square roots is the condition that that area inside the square root, has to be greater than or equal to 0, and the side length must be greater than or equal to 0. So what this is saying, this condition, is that the number inside the square root, must be positive, and the results or answer must also be positive. So whenever you're dealing with square roots, you can only get positive results, and 0 is included in that. So I'll show you an example off here to the side. Let's say we had the square root of 16, and that involves us having to imagine that we have a square with the area 16, and we're trying to find the side lengths. So what would be the side lengths that you could multiply together to make 16? Well, both of those side lengths have to be the same. It can only be the same number. And 4 is the only number that would fit into that request. So 4 times 4 would give you 16, and that's why 4 would be the side length. However, you wouldn't be able to come up with the results. For example, square root of 16. You wouldn't be able to say, oh, the side length -4 can make that square happen, because in reality, if you think of side lengths of squares, you can't have negatives as a side length. You can't have something with a negative length. That doesn't exist in our world. So even though negative 4 times negative 4 can give you an area of 16, it doesn't work in our definition of square roots as a side length. So you can't have negative 4 as an answer. So this is never going to be possible. You can't get square root of 16 equals negative 4. You can only get square root of 16 equals positive 4. Some of you may remember there is another way of writing square roots that doesn't involve the funny looking similar division looking symbol. Another way of writing a square root of a number, like square root of a, is to write a to the 1/2 power. A to the 1/2 power. So writing something to the half or a third or a quarter power or a fraction power, when you have fractional exponents mean radicals, or mean the opposite, that you do the opposite, you cancel out opposite operation of a whole number exponent. So you can think of square root of 4, you can rewrite this as 4 to the 1/2 power, or square root of 36, you can rewrite it as 36 to the 1/2 power, where basically a to the 1/2 power is the inverse operation of a to the 2nd power. So now that we've talked through the definition of square roots, let's talk a little bit about the rules or theorems that square roots have. Just like when we talked about exponent rules, radical rules also exist. So let's look at the square root of a times the square root of b. That's always going to be equal to the square root of a times b. So if you think about radicals as a type of exponent where you have halves, you can think of it as like a to the 1/2 power times b to the 1/2 power. And the same thing happens with that exponent rule, where you can rewrite this as a times b and then have the 1/2 power outside of that parentheses, which essentially means having that square root symbol outside both of those numbers. Okay, so examples of where that comes into play would be, let's say we had the square root of 2 times the square root of 8. You could think of them as 2 to the 1/2 power times 8 to the 1/2 power, and you can rewrite it as 2 times 8 to the 1/2 power. And simplify that inside to become 16 to the 1/2 power, which incidentally is the square root of 16, and we could simplify that a little bit more to give us 4. Basically, we've seen this before with an exponent rule, so I'm just going to, in the proof section, remind you what that rule was, that when you have a to the nth power times b to the nth power, that is equivalent to a times b first within parentheses and both of them to the nth power. So the exponent rule allows you to rewrite it this way, so that's our proof of why we can rewrite radicals that way. Next, we have our square root of a over square root of b, equivalent to a big square root over a divided by b. So an example of that would be, let's say we had the square root of 12 over the square root of 3, and individually that looks like you can't really square root either of them, but with this theorem or rule, you can rewrite it as having a big square root outside of the 12 being divided by 3 and apply that division first, which means you can simplify the inside to become 4, and that's a whole lot easier to find the square root of. The square root of 4 is 2, something we wouldn't have been able to do if we didn't know this theorem. So rundown of why this can happen, we can interpret the square root of 12 as being 12 to the 1/2 power. We can interpret the square root of 3 as being 3 to the 1/2 power. And if we think about our exponent rules, we can rewrite this as being 12 over 3, both of them to the 1/2 power, 4 to the 1/2 power, which was 2. And the rule that this depends on, the reason we can do this as radicals, is because we learned about an earlier exponent rule where if you have a to the nth power and b to that same nth power, you can rewrite them as being a divided by b to the nth power. And these are exponent rules that if you are unfamiliar with, you may want to look back at entry number 54. Okay, exponent rules. Now, not all exponents and radicals can be conveniently simplified to just a whole number like we did here with 2 and we did here with 4. That doesn't happen often. So the way we quote-unquote simplify radicals, the simplest form of writing roots, is to replace any perfect squares inside the root sign with the perfect square result outside the root sign. So what I mean by perfect squares is I mean a number that will have a whole number result when it is square rooted. A perfect square has a whole number result when it's square rooted. So, for example, a square root of 4 has a perfect whole number 2 as a result. A square root of 16 has a perfect whole number 4 as a result. So if you see any perfect squares inside of the root sign, you want to take that result and put it outside of the root sign. The final thing to watch out for when you're writing a square root in its simplest form is you don't leave any square roots in the denominator. Don't leave any square roots in the denominator of a fraction. So you can't have, your simplest form answer, you can't have 1 over square root of 3, for example. You don't want to leave it like that. Okay, that's a no. Look at a couple examples of this. So the first one is the square root of 1,800. Now the square root of 1,800 can be rewritten as the square root of 18 times the square root of 100. So you want to, when you're simplifying square roots, you want to look for perfect squares, right? And once I saw the 100, I know that there's the square root 100 in there, and so that's the two that I want to separate it into first. And so square root of 18 times square root of 100, you can square root 100 into a perfect whole number, so that's going to give you square root of 18 times 10, because this is a nice perfect square number. Then we want to see if there's anything else we can do with the square root of 18. And if we factor it out just a little bit more, look at its factors, there's also 9 in there times 2. So we can rewrite square root of 18 as the square root of 9 times the square root of 2. The square root of 9, that's a perfect square. That gives us 3. So we have 3 times square root of 2 times 10, and that's close to being our simplest form. Then we multiply the two whole numbers together to get 30 times the square root of 2. And we always write the whole number in the front and the radical behind that. Let's look at the square root of 2 over the square root of 6. This is our next example. We know that because of a property of the radicals, we can rewrite this as a big square root around just a fraction 2 and 6. And so that can help us simplify this further. 2 over 6 can simplify to 1/3. And then we can use another property of radicals to give the radical to both numbers in the fraction. So then the 1 gets the radical and the 3 gets the radical. We split it up again because when we look at the square root of 1, that's basically the same thing as 1. So square root of 1 is a perfect square. and that can give us 1 as a result, and then we're left with just the square root of 3 on the bottom. However, we just learned that the simplest form of a radical can't have a radical in the denominator, so we don't want that radical in the denominator. The only way we can get rid of that is by writing 1 over the square root of 3. We can multiply it by 1. We can multiply it by 1, or something equivalent to 1. Something equivalent to 1. You can always multiply something by 1 and still have it be equivalent to itself. So then let's look for things that if you multiply it, and it can make that radical go away. And a number that can make a radical go away is that radical again. Remember, the opposite of a square root is squaring something, so if you multiply something by itself, that would make that radical disappear. And so 1 can be rewritten as, we can think of 1 is the same as the square root of 3 divided by the square root of 3, because when you have the same thing top and bottom, that cancels out. So we can write this as 1 over the square root of 3 times the square root of 3 over square root of 3, and that will help us get rid of this radical on the bottom of the fraction. So then when we multiply it, we get 1 times square root of 3 on top, which is the square root of 3, and then square root of 3 times square root of 3 on the bottom gives us just 3. So our simplest form of this fraction would end up being the square root of 3 over 3. The last thing I want to cover today is the idea of combining standard form roots. So what that means is if you have two numbers with the same radical in them, like the 3 square root of 7 plus 5 square root of 7, and they both have radical 7 in them, how can we add them together? So I want you to think of radicals as multiplication, right? As an exponent, so something's being multiplied together. What this is saying is basically we have 3 radical 7s, and this is saying we have 5 radical 7s being added together. And so when we add them all up, we can add them all up. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. So we can say there are 8 radical 7s here. So basically, it's like adding 3x plus 5x. You can add them together and get 8x. 3 radical 7 plus 5 radical 7 is the same as 8 radical 7. Here's another example. Let's say we have negative 2 square root of 11 plus 4 square root of 11. Now, negative 2 square root of 11 plus 4 square root of 11, we can think of it as negative 2x plus 4x. They are sort of like terms. You just add the front two numbers together. Negative 2 plus 4 is positive 2, 2x. But here we have radical 11, so negative 2 square root of 11 plus 4 square root of 11 will end up giving you 2 square root of 11 as an answer. Can we not combine standard form roots? Well, let's say we have an example like 5 square root of 11 plus 11 square root of 5. Well, these are two different things because this one is saying there are 5 square roots of 11 being added together. There's 5 of them. And this one is saying there are 11 square roots of 5. Well, I'm not going to write all of that out, but you can imagine 11 of these here. You can't combine the two of them together because it's not the same number inside the radical. They're not the same type of object. It's like saying, let's combine these apples together with these oranges. But they're not the same thing. You can't just group them together. So the simplest form would just be this. You cannot simplify it any further.